Well, welcome to the Tuesday afternoon session. I'm Barbara Kiefitz, and I'm very happy to be here and to have the honor of introducing, I think, the first Fields medalist to speak at this meeting, who is Charles Fefferman, sorry.
Charlie.
Who was born in Washington, studied at the University of Maryland, at Princeton University, wrote a dissertation for Eli Stein, went to the University of Chicago, came back to Princeton. You can't hear us? Oh. Oops, can you hear me now? It's on.
Yes, we can hear you on Zoom.
Thank you, but I don't, why don't I shout? That's perfect. Okay, all right. Where was I? All right, dissertation for Eli Stein. Moved on, won the Fields Medal, won many other awards. The one that appealed to me the most is that he was the inaugural winner of the Alan T. Waterman Award and helped make it famous. And he is going to speak to us today on tunneling in magnetic fields.
So
take it away.
Thanks, Barbara. Oh, thank you. Thank you. Okay, so let me ask. So we've had trouble with microphones, and I'm speaking through this thing. Can everybody hear me clearly? Is it okay? Great. Okay. Thank you for the invitation. It's always a pleasure to come back to Fields. Now, in this meeting, we've already heard several very beautiful survey talks. This is the opposite. I'm going to be talking about one problem about which there was no progress for a long time, and finally now there is progress. Okay, and so the purpose of the talk is to explain that. Okay, so the executive summary is that magnetic fields alter quantum mechanical tunneling in strange, unexpected ways. Tunneling is a basic phenomenon of quantum mechanics. I'm going to insult the experts by giving elementary explanations of lots of things. Okay, so the plan for today's talk is that there's going to be a quick review of tunneling from undergraduate quantum mechanics, after which will come a brief discussion of the rigorous results that were proven in the 80s about ordinary tunneling. But then we're going to add a magnetic field into the mix, and then review some old conjectures and results regarding tunneling with magnetic fields. But it turns out that those old conjectures are at least very probably wrong, as you'll see. So then there will be some new results and new conjectures and some unsolved problems. I have no idea how long all of this is going to take, but I'm very determined to finish within the time limit. So let's see what happens. Okay. Okay. So we're going to be working with two-dimensional systems, and so our Hamiltonians are going to act on L2 of the plane. I seem to notice that the world is three-dimensional, but we haven't gotten to 3 dimensions yet. So this is two-dimensional. Okay. So let's do a little review of undergraduate quantum mechanics. Okay. So tunneling is the following thing. Imagine that you have a table with 2 pockets, and you place a little particle in one of the pockets and then go away. If you come back later, you may discover that the particle is in the other pocket. That's tunneling. Okay. Mathematically, here's the formulation. So we have a Hamiltonian. It's a Schrödinger operator. So we have minus Laplacian plus a potential. The potential is lambda squared times something or other. Lambda is a coupling constant. Okay. And VL and VR are potentials, each less than or equal to 0, and each supported in its own disk, and those represent the 2 pockets. Okay, so let's say one of them is exactly a translate of the other by some vector, and I have here that the vector here called xi has length at least 10, so that the pockets are well separated. They, for example, don't overlap. Okay, now, all right, just terminology, then lambda squared times either VL or VR are called the one-well potentials. And if I add those together, you have a two-well potential. That's the terminology. Okay, Now, I'm going to suppose here that the one-well potentials are even about the centers of their supporting disks. That's not necessary for all the results, but let's not be greedy. Okay, now tunneling has to do with the two lowest eigenvalues of the Hamiltonian for the two-pocket potential. Okay, so I'm calling those E1 and E2, sometimes with a lambda, sometimes not. So E1 and E2 are the two lowest eigenvalues of that Hamiltonian. And according to undergraduate quantum mechanics, the timescale on which tunneling occurs is essentially 1 over the distance between those two eigenvalues, and 1 over the difference. And that difference is called the spectral gap. Okay, so those are the characters in the drama. So the spectral gap and the timescale in which tunneling occurs is 1 over the spectral gap. Okay, well, how big is that spectral gap? There is a simple-minded perturbation theory. It's misleading for me to call it first-order perturbation theory, but I will because I don't have a better description. There's some simple-minded approximation in which one guesses that the spectral gap is twice some number called the hopping coefficient. Okay, so I'm about to describe what the hopping coefficient is. All right, so here's the definition. So let's say phi L is the ground state eigenfunction of the one-well Hamiltonian for the left-hand well. And guess what? We're going to call the ground state eigenfunction for the right-hand Hamiltonian. We're going to call it phi R. And because the two potentials, the left potential and the right potential, are simply translates of each other, the same is true of the ground state eigenfunctions. Okay? Then the hopping coefficient is given by the formula on the slide. So we multiply the left-hand, all right, there's a complex conjugate, but we multiply together the two ground state eigenfunctions, the left one and the right one, and we multiply by the right-hand potential. I put in a minus sign because I'm going to be talking about the order of magnitude of rho, so I would like rho to be positive, but that's I mean, that's not the standard convention. If you read textbooks or the literature, that minus sign won't be there. Okay, so that's the hopping coefficient. Okay, a little bit more detail about this simple-minded perturbation theory. If phi L is the ground state eigenfunction for the left-hand potential and phi R for the right-hand potential, then we would like to understand in terms of those the two lowest eigenfunctions for the two-well Hamiltonian, and they're simply given up to a normalizing constant by either adding together the left and the right ground states or subtracting them. So the adding them together gives you the ground state, subtracting them gives you the first excited state. Okay, in particular, the ground state is even about the midpoint between the two potential wells, whereas the first excited state is odd about, with respect to that reflection. Okay, well, that's what comes from simple-minded non-rigorous perturbation theory. What's proven? So the rigorous results go back to the 80s, and they are the following. The hopping coefficient decreases exponentially in the coupling constant lambda as shown, and the difference between the two lowest eigenvalues, the spectral gap, is indeed approximately twice the hopping coefficient. And these are just the simplest results to state. Much, much sharper results were proven back in the 80s. But again, this, I mean, the purpose of this talk is not to give the sharpest possible results. So let's be content with these. Okay, in particular, notice that as in the simple-minded perturbation theory, the ground state is even and the first excited state is odd. All right, all right, some credit as credit is due. I think the theorems are due basically to Barry Simon and to Helfer and Scherstrand from the 80s. I imagine other people proved useful results there. I'm not an expert on the old literature, or for that matter, on the new literature. Okay, so that's the review of basic tunneling from undergraduate quantum mechanics together with what's rigorously known. Now let's introduce magnetic fields. Yes? Yes, yes, one can vary the separation also, but today let's not. Yes, yes. Oh, by the way, so this illustrates something. Please feel very free to interrupt, and it's conceivable that if you ask a question, you will get an answer. Okay. Okay. All right, so now magnetic fields. Okay, so let's suppose that there is a constant magnetic field perpendicular to the plane in which our particle lives. In that case, the Hamiltonian changes. Instead of minus the Laplacian plus a 2-well potential, we now have the thing in the red box. We have a modification of the gradient before you square it, and this is a manifestation of the great granddaddy of all gauge fields, okay? So, well, that's the Hamiltonian which one gets out of an elementary physics textbook. Okay, so, all right, H is now going to be written in this slightly more compact form. I introduced the vector x perpendicular, that's just x rotated by 90 degrees, and that denotes the previous guy. So look at the previous guy, and now here's the way it's denoted in the upper box. And there are corresponding 1-well Hamiltonians, and they're in the lower box. And the kinetic energy doesn't change, only the potential energy. Okay, so we have a magnetic 2-well potential, and we have magnetic 1-well potentials. Okay. All right, so the ground state eigenfunctions of the 1-well Hamiltonians are going to be called phi L and phi R. And because the two potentials are just translated from each other, their ground state eigenvalue will be the same. And we'll call it minus E, so that E again is positive. Okay. And we, let's see. All right, before I say anything further, I want to say we're going to work in a regime in which the effects of the potential and of the magnetic field are comparable. We don't want either one to be negligible compared to the other. And the way that that happens is that the magnetic field strength should be some constant times the coupling constant lambda. And so we're going to take lambda to infinity while beta stays fixed. So we have a strong magnetic field and a strong potential well, and that's the relationship between them. And so simply changing the letter capital B for the product beta times lambda, we have the 3 formulas in the box for the for the 2-well potential and the 2-well Hamiltonian and the 2 1-well Hamiltonians. Okay, and now the question that I want to discuss today is what happens to tunneling in a strong magnetic field? More precisely, for the magnetic 2-well Hamiltonian, we want to understand the ground state, the first excited state, their corresponding eigenvalues E1 and E2, and in particular the spectral gap E2 minus E1, and the hopping coefficient rho. That's what we want to know. As before, rho is defined by the formula that you saw before. There it is, okay? And as before, tunneling between the 2 wells takes place on a time scale essentially 1 over the spectral gap. And as before, there's some simple-minded first-order perturbation theory that predicts that the spectral gap is twice the hopping coefficient. Well, that's fine, but now how big is the hopping coefficient? So I've written here natural old conjectures. I think I should carefully define the word conjectures. I have no idea whether anyone wrote this down, but simply, given what people knew in the 1980s, this is the obvious extrapolation of what was known. Okay, so one would think that, as in the non-magnetic case, that the hopping coefficient is exponentially decreasing in the coupling constant lambda with beta fixed, and that the spectral gap is approximately twice the hopping coefficient. Okay, one would guess also that the ground state of the 2-well Hamiltonian is even in an appropriate sense. So because gauge transformations are floating around, one has to be a little careful. Let's say the 2 wells are symmetric about the origin. One of them lies to the left of the origin and the other one lies in equal distance to the right of the origin. And then even simply means even and odd simply means odd. So one expects that the ground state is even and the first excited state is odd, as in the non-magnetic case. Okay, well, that's what one expects from simple-minded non-rigorous models, what has been proven? Well, as in the non-magnetic case, it's been proven long ago that rho, the hopping coefficient, and E2 minus E1, the spectral gap, are at most some exponentially small quantity in lambda. So those are upper bounds, okay? These authors gave related results, okay, Matsumoto, Erdős, and Nakamura, and they analyzed the decay of the one-well eigenfunctions in the 90s. Maybe I'll come back to that. However, until a few years ago, there were no known lower bounds for either the hopping coefficient or the spectral gap. So for example, no one knew how to rule out the possibility that the spectral gap is 0. Okay, so that's a pretty severe lack of understanding of the lower bounds. Okay, so what I'd like to do now is explain why the problem of finding lower bounds is hard, and then what would happen if the spectral gap were 0. Okay, so here's the central difficulty. The kinetic energy term, which you see on the slide, the kinetic energy term is not a constant coefficient operator. Just look at it. It isn't. It doesn't commute with translations. Instead, it commutes with translations only up to a gauge transformation. Okay, and as a result, whereas in the non-magnetic case, the two eigenfunctions phi left and phi right are simply translates of each other, in the magnetic case, the left and right eigenfunctions are translates of each other multiplied by some oscillatory exponential factor. Okay. Therefore, instead of the previous non-magnetic formula, which you see at the top of the slide, the hopping coefficient is now given by an integral which you see in the red box. Now, all right, well, that exponential factor, e to the I, blah, 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 messes everything up. In particular, in the magnetic case, our hopping coefficient is defined by an oscillatory integral whose phase function has no critical points. Now, if you remember from basic analysis, when you're confronted with an oscillatory integral, what you're supposed to do is look at the critical points, and you will find that the dominant contribution comes from the critical points, and everything else is negligible by comparison. In this case, I'm sorry, there are no critical points. That isn't going to work. Yeah, that's not good. Oops. Okay, so that's why the problem is hard. Okay. Okay. Well, all right. Now let's see what would happen if the spectral gap were 0. All right. Well, in that case, the time scale 1 over the central gap, over the spectral gap, sorry, would be infinite, and that means that tunneling would not occur. By the way, I'm advised that tunneling has 2 L's, only in Canada. Okay. 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 So. All right, we'll have other interesting linguistic events on the slides very soon. Anyway, so tunneling would then simply not occur. And so the ground state eigenspace for the 2L Hamiltonian, instead of being one-dimensional, would be two-dimensional. It would be spanned by 2 wave functions that I call psi left and psi right. Psi left is strongly concentrated in the left-hand well, and psi right is strongly concentrated in the right-hand well. And if a particle is in the state Psi-L, it will just stay there. It will not tunnel into the right-hand well. And similarly, if our particle is in the state Psi-R, it will stay there without tunneling to the left. So that's what would happen if the spectral gap were 0. Well, we will see that this can actually happen. So I'm going to show you a counterexample in which that stuff happens. Tunneling is completely suppressed. The spectral gap is 0. And stranger things than that happen also. All right, so we'll see that tunneling can be completely suppressed by a strong magnetic field. Okay, so to present the counterexample, I want to first mention a positive result, and this is, I think, the first progress since the 80s, well, in fact, since the beginning of time, on lower bounds. I should say that this result, as well as, I'm talking about joint work with Jacob Shapiro and Michael Weinstein. And that's true of all the new results that I'm going to talk about. I should have mentioned that at the beginning. Okay, so here's our theorem from a few years ago. Suppose that the potentials VL and VR are radial about the centers of their supporting disks. Then the natural conjectures are all true. Okay, I'll explain in a little more detail in just a moment, but I want to say, in addition to the number of L's in tunneling, here's a more serious mistake. There's an additional hypothesis. The potential wells, each potential well should look like a bowl rather than a Mexican hat. So I don't want to be too precise and get bogged down, but all right, in lots of interesting cases, if the potentials are radial about the centers of their supporting disks, then the natural conjectures are true. And in particular, indeed, there are exponential upper and lower bounds for the hopping coefficient, and the spectral gap is approximately twice the hopping coefficient. And furthermore, the two-well ground state is even about the center, and the first excited state is odd, as expected. That proof is based on what the slide says is a tricky special function identities that let us write rho as the integral of a positive quantity. I think maybe that's that's not sufficiently chest beating. I think these identities are miraculous. Anyway, so although rho is initially given as this horrible oscillatory integral with no critical points, nevertheless, in the radial case, you can rewrite it as the integral of a positive quantity, and life is good. Okay, Helfer and Kochman then combined those special function identities with refined WKB in order to give precise asymptotics for rho, and Morin simplified the whole thing. So by now this is in very good shape. Once rho, the hopping coefficient, is well understood, the rest follows easily enough. But as it says on the slide, the whole discussion collapses if the potentials are not radial. And so if the potentials are not radial, again, until recently, absolutely nothing was known in terms of lower bounds. Okay, so that's the background. And now I would like to explain the counterexample of Shapiro, Weinstein, and me, showing that tunneling can be completely suppressed. So we'll see that the hoped for lower bounds on rho and the spectral gap depend very sensitively on little tiny perturbations of the potentials. And so here's the counterexample. Remember, well, look at the slide. That's our Hamiltonian. Beta is fixed, lambda is enormous. I'm going to describe what VL looks like, and then of course VR is simply its translate. All right, so to construct VL and VR, to start with, we're just going to take a radial example. So in this illustration, imagine that we're looking down on the table. The white space is the flat table, and as one of the pockets is slightly depressed under the table, you see green, and at the very bottom, you see dark green or black. Okay, that's what this picture is supposed to represent. So this is a radial example in which everything is as we expected, thanks to the previous results. But now we're going to perturb it by adding sophons. So these come, I don't know if you happen to have read the wonderful science fiction novel by Cixi Liu, the three-body problem. Sophons are the English translation of the following Chinese word, supplied to me by a friend who also assured me that I don't have it upside down. Okay. Okay. Recall from the science fiction novel, sophons are little tiny things, which, however, cause lots and lots of trouble. Okay. So our sophons are going to do the same thing. Our sophons are going to be potentials W less than or equal to 0, supported in little tiny disks of radius delta. Delta is exponentially small in the coupling constant lambda. And furthermore, not only is the absolute value of W small, but the W and its derivatives up to order 100 are incredibly small, the less than or equal to, let's say, delta to the 100. So each sophon is really, really tiny, and yet by carefully placing a few sophons, we can arrange that the that the spectral gap is exactly 0 and tunneling is suppressed. Okay, here's how to place the SOFONs. Okay, so the little red dots are the SOFONs. So around each potential well, there are 4 SOFONs. And we're going to make little tiny adjustments in the positions of the SOFONs. And by either making little tiny adjustments in the positions of the SOFONs or by making little tiny adjustments in that parameter beta, one can produce a case in which tunneling is completely suppressed. Moreover, something even stranger than that happens, namely, you can arrange that although we expected that the ground state is even and the first excited state is odd, in fact, one can arrange that the ground state is odd and the first excited state is even. And once that happens for one potential, it occurs for all potentials, maybe having nothing to do with these SOFONs, just for all potentials near that in any reasonable form. So it can happen that, so this can genuinely happen. One can observe this effect in principle by looking at the midpoint between the 2 potential wells. If the ground state were even, you would expect some positive probability that a particle in the ground state would end up there. So you keep looking and occasionally you will see a particle at that location. Whereas if the ground state is odd, you will never see a particle in the midpoint. So there's at least a Gedanken experiment one could perform to detect this effect. Okay, similar examples. I've spoken about the I've spoken about the spectral gap, but similar conclusions apply to the hopping coefficient. Okay, now, all right, note SOFONs are tiny, but they do depend on lambda. And so our counterexample suggests, but does not prove, the conjecture on the next slide. And so the conjecture is that if you fix beta, this ratio between the magnetic field and the coupling constant lambda, then there exist potentials VL and VR close to radial and translates of each other, such that the spectral gap for the magnetic Hamiltonian is equal to 0 for an infinite sequence of lambdas tending to infinity. That's a natural conjecture, but we don't have the proof. To produce such potentials, our idea is to start with radial potentials, but then add infinitely many ever tinier SOFONs to correct at infinitely many values of lambda. We hope that will work, but it fights back considerably, and we don't know whether it actually works. Okay, well, so much for counterexamples. Now let's discuss positive results for non-radial potentials. Okay, so again, the results are due to Jacob Shapiro, Michael Weinstein, and me. These are the first known lower bounds in the non-radial case. Okay, so for fixed beta and for fixed VL and VR, what we're going to do is to derive lower bounds on the hopping coefficient and the spectral gap for most large lambda. This is a question that wouldn't have been natural before the counterexample, but after the counterexample, you'd better not look at arbitrary large lambda, you'd better hope for most large lambda. So what do we mean by most large lambda? And what I mean is most large lambda means lambda outside a set of density 0. If you have a measurable subset of the positive real axis, then for sufficiently large numbers lambda, you can intersect E with the interval from 0 to lambda. You can find the measure of that intersection. You divide that by lambda. And if that tends to 0 as lambda tends to infinity, then E is said to have density 0. Okay, so that's a standard definition. Okay, under suitable conditions on non-radial potentials and this parameter beta, we're going to give lower bounds for the hopping coefficient and the spectral gap. And those lower bounds will hold for all lambda outside a set of density 0. Okay, now the suitable conditions and the lower bounds depend on a small parameter epsilon. So as epsilon gets smaller, the assumptions get stronger, but also the conclusions get stronger. Okay, so here are the assumptions. So let's say I give you a small number epsilon. What am I going to assume about the potential VL and the parameter beta? I will say that they satisfy hypothesis epsilon if the following hold. So here are the conditions. First bullet point, the potential is C3. Okay, fine. The potential is less than or equal to 0. Okay, fine. The potential is supported in the unit disk. Okay, fine. The potential has a unique minimum at 0. Okay, fine. The Hessian of the potential at 0 is the identity matrix. Oh, damn, we would much rather not have that. I'll get back to that. But in any event, notice so far, the potential is not radial, but nevertheless, there's this small vestige of radial in which we want the Hessian at the origin to be a multiple of the identity. In fact, let's say exactly the identity. And finally, the size of this coupling, the size of this parameter beta it should be small enough by a constant determined by epsilon. So those are the conditions. All right, if those hold, then the spectral gap vanishes for at most a discrete set of lambdas, and similarly for the hopping coefficient. Okay, the second theorem says that suppose that hypothesis epsilon holds, then except for a bad set of lambdas of density 0, one finds that the spectral gap is bigger than e to the minus lambda to the 1 plus epsilon. So we would like to have e to the minus lambda. We have instead e to the minus lambda 1 plus epsilon. Okay, so I would say these theorems have their strengths and their weaknesses, but they are the first results for non-radial potentials. Okay, and similarly for the hopping coefficient. Okay, now let me mention a few open problems. So first of all, these two positive results are only first steps. We'd certainly like to remove the assumption that the Hessian at the origin is the identity, and I consider that low-hanging fruit. I think if we put in enough work, we will simply get it. I would be surprised if not. The assumption that the coupling constant beta is small, that may well be within reach. I don't know. I'm not as confident as the previous thing about the Hessian, but I think we have a reasonable chance of doing that. We'd like to show that for typical large lambda, the eigenvalue gap and the hopping coefficient is at least e to the minus constant lambda rather than e to the minus lambda to the 1 plus epsilon. And we've got a shot at that. I don't know. What I think is very hard is the problem of understanding the asymptotics of the sequence of lambdas for which the spectral gap is 0 when tunneling is suppressed. That will take big new ideas. At this stage, it's already a challenging problem to show that the sequence of lambdas it might be infinite, let alone to understand its asymptotics. So that will be hard. There's, of course, the problem of passage to 3 dimensions. There are other problems, but let's stop now. And I thank you for your attention.